of function g of x is given by the following formula, where k and m are constant. So k and m are just some numbers that we don't know, and our g of x is defined as follows. And we wish to find all values of k and m so that g of x is differentiable on all real line, the entire real line. Write none if there are no such values. Okay, we do not need to simplify the answers, but we have to show the work. So how we approach these kind of questions where you have to make a piecewise function differentiable is a really two-step process. The first thing is you want to make sure that g of x is continuous. And the reason for this is that if a function is not even continuous, then it's not going to be differentiable. We want to make sure that intuitively that the function is at least connected before we even talk about the notion of slope or tangent line or things like that. Like if g of x looks like this, so if this is what g of x looks like, it's not continuous, then the finding the tangent line at this point is really awkward. Maybe you can try thinking about, oh, tangent line from the left looks something like this, but I mean, that's not really what we want. We really want a tangent line that encompasses what's happening near this point from left and right. And if you have discontinuity, then that's a hard concept to reason about. So we really want to make sure g of x is continuous, and that's going to be step number one. And here, the continuity-wise, you don't really have any problems to the left of 5 and to the right of 5. So to the left of 5, I mean, this is exponential function that's always well defined. To the right of 5, you might be concerned that maybe inside the square root, you have a negative number. Like when you have square root of -1, that's now imaginary and you might have problems. But thankfully, you don't get anything like that because x is greater than 5, so the thing inside square root is always positive. So you don't get any problem to the left of 5 and to the right of 5. The only question is what happens at x equals to 5. So at x equals to 5 is really the only concern because you're switching from one branch to another branch, and if you mess it up, then maybe at x equals to 5, you might have a problem like this. So we want to ensure that that doesn't happen. So what do we want to check? Well, we want to check that the function value from the left at 5 and the function value from the right at 5 agree. So we want to check the limit as x approaches 5 from the left, this minus sign, of g of x, and we want to look at limit as x approaches 5 from the right of g of x, and we want to make sure that these two are the same. So let's start by looking at the first one. So here we're approaching from the left, so you're looking at this equation because x is less than 5, and as x is becoming closer and closer to 5 from the left. So when x is 4.9, 4.99, 4.999, well, the thing inside the exponent here, this negative x, is, or really this x here, is becoming closer and closer to 5. So we really approach k times e to the negative 5 plus 5, and e to the 0 power is 1. So we get k from the left. Let's see what happens to the right. Well, when x is more than 5, then you're going to be plugging in things here. So x is greater than 5, and as x gets closer and closer to 5, like 5.1, 5.01, 5.001 from the right, we see that this x gets closer and closer to 5, so we get m plus square root of 9 or m plus 3. So the fact that g of x better be continuous for it to be differentiable is giving us the information that k must equal m plus 3. So this is one information we have. I guess technically I should also point out that not only do you want the limit from the left and limit from the right to agree, but you also want to make sure that g of 5, which might be a separate concept from these two. So we want to make sure that g of 5 and these two values. So we want to make sure that all three of these are equal. So that's technically what you want. Because if you think about it, if your g of x looks like this, at x equals to 5, then limit from the left is and limit from the right might agree, but the function value is not the same. So technically you have to make sure that all three of these are equal, but I mean that's totally okay because g of 5 is what? G of 5, well, that's when x is 5, so you plug it in here and you get k here. So g of 5 is k, so we just want to make sure k and this and m plus 3 all agree. I mean, that's really the same as just k and m plus 3 being the same. So that's what we get from step 1. Step 2 is now actually make g of x differentiable. So this might be a bit confusing. I know all we want is make g of x differentiable, but continuity is a necessity. It's a necessary requirement to satisfy before we even talk about differentiability. So you technically have to do step 1 before. So now let's look at step 2 and see what kind of relationship we get. Well, now we actually have to differentiate things. So we know from the left it's this, and from the right it's this equation. So we have to differentiate both. So let's do so. So maybe I'll do it here just so we can see the equation at the same time. So from the left, so let's look at it from the left. So x less than 5. Let's think about what g prime of x is. You might be asking, why am I not writing less than or equal to 5 since we have less than or equal to here? Well, at x equals to 5, g prime at 5 is actually a pretty delicate matter, because if you want to talk about g prime at 5, you really have to look at the slope from the left and the slope from the right and see if they agree and things like that. So if you want to talk about g prime at 5, it's actually not just sufficient to look at this branch, but you actually have to consider this branch as well, which we are about to do. But for now, or if you're just differentiating this, you can actually only make argument for x less than 5. So let's do x less than 5. When I differentiate this, well, you have to use the chain rule. This negative x plus 5 is your inside function. So we get k e to the something. When I differentiate e to the something, I get e to the something, but something is negative x plus 5. And then by chain rule, I have to differentiate this inside function. So differentiate minus x plus 5 and multiply by that. So we get this times minus 1. What about x greater than 5? Well, here g prime of x, when I differentiate this, well, m is just a constant, so that becomes a 0 when I differentiate it. Square root of x plus 4, if you're uncomfortable, maybe write it as the power, write it as x plus 4 to some power, 1/2 power. So now we can use the chain rule. We have something to the 1/2 power. How do you differentiate something to 1/2 power? You can now use the power rule. So something to 1/2 power, 1/2 drops down. Something to the 1/2 minus 1. You subtract 1 from the exponent, you get negative 1/2. And then by chain rule, I have to differentiate the inside function and multiply by that. Well, inside function is just 1. So you actually don't really get any changes here by chain rule. And now let's think about this. You want to make g of x differentiable. And here again, at x equals to 5, you better check that slope from left and the slope from right are the same. And how do you guarantee this? Well, slope from left is when you're looking at this x less than 5, and as x gets closer and closer to 5, this thing becomes k times e to the 0 times minus 1. So we get minus k here. And from the right, we're looking at this thing, and x is becoming closer and closer to 5. So we get 1/2 times 9 to the negative 1/2. And 9 to the negative 1/2. So make sure you don't get confused. Negative 1/2 just means you move 9 to the bottom of the fraction and just make the exponent positive. So it's 1 over 9 to the 1/2. 9 to the 1/2 is 3. So this is 1/3 times 1/2. So that's 1/6. So you know negative k is 1/6. Since you want the slope from the left and slope from the right to be the same. So that tells you that k is negative 1/6. So we found k. Now remember that we had this equation from continuity constraint. So we know from this equation, it's getting a bit messy, but hopefully you can follow, is negative 1/6 plus m plus 3. And from this equation, we see that m must be negative 1/6 minus 3 or negative 19 over 6. So our final answer is that k has to be negative 1/6 and m has to be negative 19/6.